Welcome to Chapter 2, Variables, Operators, and Modularization. By the end of this chapter, you'll be able to declare and use variables and constants, perform arithmetic operations, describe the advantages of modularization, modularize a program, and describe the features of good program design. Variables are values stored in RAM that can change. Think of them as temporary placeholders your program uses for calculations, like int x equals 2 or string x equals Brandon. Constants are variables that don't change, staying the same for the entire program's execution. In C++, that's const int num equals 2, in Java it's final int num equals 2, and in Python it's simply num equals 2, since Python doesn't enforce constants at the language level. Numeric types range from byte, just one byte holding -128 to 127, up through short, integer, and long, each doubling in size and range, plus float and double for decimals, offering roughly 6 to 7 and 15 to 16 digits of precision respectively. Alphanumeric types include char, a single Unicode character, and string, whose size depends on length and encoding. Boolean holds true or false in as little as a single bit. Every data type defines what values a variable can hold, how it's stored in memory, and what operations you can perform on it. Here are the primitive types you'll actually use most in this course, with real code. Integer. Int x equals 123,456. Float. Float x equals 123.456778, for roughly 6 to 7 digits of precision. Double. Double x equals a longer decimal, for roughly 15 to 16 digits of precision. Char. Char x equals b, a single character. String. String x equals Brandon. And Boolean. A flag set to 1 or 0, behaves the same as setting it to true or false. Naming conventions vary by language and use case. Snake case, my underscore variable underscore name, is standard in Python. Upper snake case or screaming snake case, my underscore variable underscore name, marks constants in Python, C++, and Java. Camel case, my variable name, is standard in JavaScript, while Pascal case serves a similar role in C# and Java. Hungarian notation, str my variable name, prefixes the type itself, used in C and Visual Basic. And contextual notation, like founded, is common for Boolean variables. Rules to remember. No spaces, must start with a letter, and always choose a name with real meaning. Before a variable can be used, it must be declared with a data type and a name, like int myvar. Int is the type, myvar is the identifier. It should also be initialized, like myvar equals 0, since a variable points to a spot in memory, and using it before initializing means it could contain whatever garbage was already sitting at that address. You'll see exactly that kind of garbled output if you try. Best practice. Declare and initialize in the same step, like int myvar equals 0. After declaring and initializing variables, assignment statements set their values, myvar equals 2, or myvar equals first num plus second num, for example. Don't confuse two very different operators. The assignment operator, a single equals sign, assigns a value to a variable, while the comparison operator, a double equals sign, compares two values instead of assigning anything. Expressions also follow right-to-left association and PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction, in that order. A magic number is a value that should be stored as a constant, but instead gets hard-coded directly into the code as a shortcut, like multiplying hours worked by 7.25 and 0.15 directly in a formula, with no explanation of what those numbers mean. The fix. Declare them as named constants first, like const double pay rate equals 7.25, and const double tax rate equals 0.15, then use those names in your formula instead. Magic numbers, avoid them. Named constants, use them. The 5 arithmetic operators, with x equal to 7 and y equal to 20, addition, x plus y, gives 27. Subtraction, x minus y, gives -13. Multiplication, x times y, gives 140. Division, y divided by x, gives roughly 2.857. And modulus, y mod x, gives 6. That's the remainder left over, since 7 goes into 20 twice, using up 14 with 6 left over. All of this still follows PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction. Modularization is the process of breaking a large program into smaller, manageable, reusable pieces called modules. Each module handles one specific function or task and works independently of the others. The payoff. Simpler design, better readability, and much easier debugging and testing, since you can isolate and fix one module at a time instead of hunting through the entire program. A program's mainline logic breaks into 3 stages. Housekeeping tasks come first. Initial steps like declaring variables, reading configuration, or initializing resources, essentially getting everything ready for input. Detail loop tasks are the core, often repetitive logic, processing input and performing calculations. and end-of-job tasks wrap things up, releasing resources, displaying results, or saving data, producing the program's final output. Modularization and the main function work together to build structured, scalable, maintainable programs. The main function gives the program one single, clearly defined entry point, while modularization breaks the complex work into smaller, reusable pieces around it. Together, they make debugging easier, support collaborative coding since different people can work on different modules, and improve overall readability and maintainability. A hierarchy chart is a visual map showing how a program's modules relate to and call one another, giving you the big picture overview of how everything fits together. In a typical structure, main sits at the top, calling housekeeping to get things set up, detail loop to handle the core repeated logic, and end of job to wrap everything up, exactly the three mainline stages we just covered, now shown as a connected chart. Before next class, modularize an everyday task into its three parts: housekeeping, detail loop, and end of job. Pick something like driving a car, washing the family pet, or baking a cake, and break it into that same three-stage structure we've used throughout this chapter. Print it out and bring it to class for review.